Hello, I'm Peter Yong-ho Kim, and I'm here to introduce our paper titled Can Natural Image Autoencoders Compactly Tokenize fMRI Volumes for Long-Range Dynamics Modeling? Our main goal here is to create a model that can process brain fMRI scans. fMRI is four-dimensional, as it is essentially a video of 3D images, and therefore is very costly to process end-to-end, because the data itself is just simply very large. Therefore, we want to introduce a method to make this process more efficient. And for that, we are going to use autoencoders. Autoencoders can compress information into compact latents with the encoder, with minimal information loss because they also reconstruct the information with the decoder. Our plan here is to use this encoder and compress fMRI volumes into a more manageable size, and use that for downstream applications. However, training autoencoders for fMRI is not an easy process. It takes a lot of effort to acquire data enough to train a strong autoencoder, and even then, that autoencoder might not work well for a different dataset. Therefore, we propose to use autoencoders that were trained with natural images, off the shelf, with the expectation that they will generalize well into fMRI images. To show that these off-the-shelf autoencoders work reasonably well for fMRI images, we compared the performance of an off-the-shelf autoencoder against an autoencoder that we trained with fMRI data ourselves. We discovered that natural image autoencoders can handle fMRI images reasonably well. Based on this finding, we propose our model, TABLeT, which stands for Two-Dimensionally Autoencoded Brain Latent Transformer. Using the frozen pre-trained encoder from the autoencoder of choice, TABLeT first tokenizes fMRI volumes. Those tokens are then processed with a simple transformer encoder, and then applied to various downstream tasks. Let's take a closer look into the tokenization process of TABLeT. We want to tokenize each of the 3D volumes from the 4D fMRI, and they all go through the same tokenization process. But since the autoencoder we are using is designed for 2D images, we have to slice each 3D volume into 2D images, and then independently tokenize them with the autoencoder. We then rearrange the compressed latents to form 27 tokens for each 3D volume in the final stage. Each frame of the fMRI goes through this tokenization process independently, each resulting in 27 tokens. These tokens are then simply fed into a transformer encoder, and the resulting representation is used for the downstream tasks. Here are the experimental results for our model. We tested our model against multiple baseline models on multiple datasets and downstream tasks, and our model performed the best in most cases. Also, in terms of efficiency, our model is better than existing methods. Compared to Swift, which is the state-of-the-art voxel-based fMRI model, our model is 7.3 times more memory efficient and 3.8 times faster during training. I want to note that this efficiency allows TABLeT to process much longer temporal sequences compared to existing models, potentially allowing it to capture long-range temporal dynamics. This may be one of the reasons why TABLeT outperforms the baseline models. Thank you for listening to this presentation. If you're interested, please check out our project page and our paper following this QR code. And if you have any further questions, please feel free to contact us.